So my name is Dave Argent. I work for Salesforce. I've been around the block a few times. I'm currently a senior SRE, and I flip-flop between being a way too technical TPM or an SRE who doesn't like Python as much as everyone else does. So that's by way of introduction. I will be talking about the dangerous Sidekick outage, which if you go on Google, you can still find evidence of it. It was, in fact, worse than you think it was. And usually I charge people beer for the privilege of hearing this story. So consider yourself lucky in this particular instance. On the other one, in order to get it past legal and PR at Salesforce, I am not allowed to mention the company associated with it. You'll probably understand why as I get deeper into the talk. So I was at ground zero for two truly major outages in a long career of online services. And really, this is some part storytelling and some parts lessons learned so that you can hopefully avoid some of the extensive pain and suffering that I have experienced in a long career of making online services function despite their best efforts not to. I have worked on some of the largest online services in the world. And like I said, as a condition of giving this talk, one of them I cannot mention by name. So I will start with the dangerous Sidekick outage. It was set in the dark days of October 2009 in scenic Palo Alto, California, not too far away from here. Long ago on a job far away from my current job at Salesforce. They also wanted to make sure that everyone understood that what I'm talking about did not happen while I was at Salesforce. It turns out that legal and PR folks can be finicky about what they're willing to let me talk about. It's almost like they know me. So I'm going to start with the dangerous Sidekick and its architecture. Danger was a wholly owned subsidiary of Microsoft. They purchased them in 2007. The Sidekick itself was a proto-smartphone. It had an integration with email clients and social networking sites and your texts, but there was no real app store. It was very much walled garden. So I'd call it a proto-smartphone in terms of you can see where you had old flip phones, and this was in the middle, and you could see where things were going towards the smartphones we have today. It had limited storage on device, with most of the data generally held in the cloud. The architecture, aka the dirty laundry, is the fact that it was running on Unix rather than on Windows Server, despite the fact that this was a wholly owned subsidiary of Microsoft. It was not running in one of Microsoft's standard data centers. This was running in a legacy data center that was the one that Danger had at the time of the acquisition. And all the customer emails, texts, photos, billing information, and everything else was stored in a relational database leveraging blob storage using a single SAN as its storage backend. And if you're paying attention, you can see the storm brewing on the horizon now. So we're now setting the scene. We had a single point of failure waiting to happen. And if you guessed that it was the SAN, you were absolutely correct. But it was worse than that because there was no valid backup. A second SAN or a NAS large enough to hold a complete backup was not funded. And there were enough disk shelves available on the large SAN to hold a full backup in theory, but the firmware version running didn't support that volume of storage. But the bottom line here is this is already an unsafe configuration. No matter how many redundant power supplies, networking interfaces, or anything else that you attach to a SAN, it's a single piece of equipment. It's a single point of failure, and it's going to be subject to a variety of failures. And since I'm here talking about a tale of two outages, the dark clouds are gathering, and they're looming overhead now, folks. And now we have successfully, if you want to call it success, turned risk into disaster. So the head of ops, I'm changing his name to protect the guilty party, but for purposes of this talk, I'm going to call him Dick. Decides that we need to take the SAN firmware upgrade to get to a safer configuration, with the objective of having a full backup on the same SAN as the primary, despite the lack, and he makes this decision despite the lack of a valid backup anywhere else. And Senior DBA refuses to do the upgrade because he declares excessive risk to the enterprise. And boy, truer words were never spoken. The head of ops, Dick, overrules the senior DBA, and a junior DBA is assigned to do the upgrade. And the upgrade, since I'm talking here, went pear-shaped. But it went pear-shaped in a really interesting way. The metadata partition of every LUN in the SAN is overwritten with random trash. And yes, that is as bad as it sounds, because this means that de facto every single piece of customer data is unavailable and the database is doing its best impression of a paperweight. It's a very heavy, very expensive paperweight, but a paperweight nonetheless. And less than 24 hours into this outage, which is before I was called, just for the record, the DB and the SAN vendors declared the data unrecoverable, and the storm is here, the waters are rising, and there is no arc. So it is time to drown. So what do we do instead of drowning? We try to keep calm and we try to see the big picture. And the big picture is that we have a 15 terabyte database with all the customer data acting like the aforementioned paperweight, with the database and the SAN vendors both declaring this unrecoverable. This isn't a good start. It gets better eventually, but this isn't a good start. But what you really learn in these situations is that leadership during a major incident is not just about remediation. It's about everything that surrounds the remediation. For example, I get called about 48 hours into this, and I get asked, Dave, what would you do if you needed to stand up another danger database in a hurry? And I'm like, this doesn't sound like a hypothetical question. What actually just happened here? And unlike everyone else I was talking to, I could see the class action lawsuit on the way. And I was like, okay, so you haven't put legal on any of the email threads yet. The first thing we're going to do is we're going to get LCA on every single one of these threads. Otherwise, we are all going to be subpoena bait. And that's not going to be fun for anybody. The next thing I did was I'm like, okay, we're going to need a third-party data recovery team on the next flight into San Francisco. If nothing else, it'll be due diligence for the upcoming lawsuit. And again, these were things that were like, oh yeah, that's a good idea. We should do that. But it demonstrates that a lot of people were getting like completely lost in the trees and not seeing everything else that's necessary in a situation of this type and magnitude. So I established a regular cadence of communication with executive leadership. I was one of the people who helped build out the recovery fleet for Project Lazarus, which is what we called it. We almost had t-shirts. I had the artwork for it, but they wouldn't fund the t-shirts because they were feeling cheap. But I had on the insignia, we had a beautiful picture of a hand coming up through a grave in front of a gravestone that said Lazarus. The thing in its hand looked suspiciously like the dangerous sidekick. And the caption for the t-shirt was going to be Project Lazarus, the second most impressive resurrection in history. But somehow that didn't go over well with the powers that be. So it never happened. And instead, you just get a story. I led the program management team that was directly coordinating recovery. It was staffed 24/7. And now we're going to put Humpty Dumpty back together again. So the secret sauce of the recovery is that every 4K page in the database in question has a GUID. And one of the few things that we had was we had something that vaguely resembled a file system map. So picture like 30 or more tower PCs in the aisles of a Unix data center, littering the aisles as the custom recovery tools that were used by Kroll, which was the third-party company that I had brought in, their tools only ran on Windows. So we had to build the Lazarus fleet because it was a Unix data center. So we stole desktops from literally everywhere possible. So about 6 weeks later, with the third-party data recovery team editing the tools on the fly as they had edge cases, we had 3 nines worth of the data back. We had performed miracles. Humpty Dumpty has been put back together again, 4K at a time, relying on these page GUIDs and the file system map. Take that, unbelievers. And about at that point in time, I think by now we've probably found a dinghy and there may be a rainbow over there. I will note for the record that because I worked in the incorrect building, i.e. the building in which some of this stuff happened, Despite everything I've told you here, I got a bad review that year. So what did we learn? There is no such thing as a safe change. Yes, it's in all caps, and I know it's boring, and I know everyone's heard it before, and people keep screwing it up, and I'm going to keep on putting it in caps until people stop screwing it up. Data integrity and redundancy, it matters. The cost of another SAN compared to the value of your enterprise is usually negligible. The time to build a disaster recovery plan is before the disaster, not during the disaster. We all frequently get this one backwards too. You should probably trust your senior technical staff. You did hire them for a reason. If you don't trust their judgment, either you shouldn't be there or your senior staff has been badly chosen. But one of these things will be true. You shouldn't compound earlier mistakes. We were in an unsafe configuration. It literally doesn't matter how we got to that point. Taking a high-risk path to get to the safer configuration introduced even more risk than doing nothing. There are a lot more moving pieces than a phone bridge or a war room. When the outage gets big enough, plan ahead for what you need for a major incident response. And CABs exist for a reason. Use them. A CAB is a change advisory board. So don't overrule your people and don't make bad decisions. So this was purely a human-driven outage. And we'll compare this one to a generic global e-commerce giants outage that was set more recently in 2018. Again, this was before my time at Salesforce, and this was one of those days that pager batteries were put to the test. Yeah, they were cell phone batteries, but give me a little bit of creative license here. So a bit about the architecture. Hundreds of internal services are involved in this site. Nearly all of them are relying on the same backend, which is arguably the largest NoSQL instance in the world. If you know who I'm talking about, you know who I'm talking about. I can't say the words, but I can say that it can take hundreds to thousands of individual calls to this database to render a single page on the site. And these are batched by many upstream services. Not all upstream services, but many of them did. And that's usually a good thing. There's a routing and caching layer in front of that database, which, to give you an idea of the sort of scale we're talking about, that was over 1,000 physical servers for North America. The routing and caching layer. We're not talking about a small number of nodes on the database. And the target response time for most requests is 10 milliseconds or less. So we're not talking about a database that is particularly, or a bunch of services that are particularly tolerant of long latency on your database calls. Any major failure to render or a 404 results in a dog page picturing a random employee's dog. And just noting for the record, there's a trade-off between fleet size and money sent. So it's understandable that the goal is to run close to the max load without impacting your availability and performance. So that's a bit of the dirty laundry about an architecture for a company whose name I can't offer you. But here's how it all goes south. A nameless sale started worldwide at noon Pacific Daylight Time rather than being staggered by time zones, resulting in a major load spike. The database in question handles the first 5 minutes of load without issue. We're all looking, it's good. Everything's working fine. Another group changes from dynamic to evergreen content a few minutes into the sale in response to the initial load spike against their web front end, which their web front end could not handle. This evergreen content, unfortunately, was never properly load tested. Some very popular items were left out of the manually populated cache layer, including the Instapot and the Nintendo Switch being two of the heavy hitters. And what was worse was we knew those were heavy hitters. We knew those were heavy hitters because they beamed us for a previous unnamed sale. Some services have large number of retries with no backoffs set, resulting in hot entities. Calls are beginning to fail on the nodes hosting these entities. With the calls failing, you end up retries getting queued. Your clients are timing out on calls, and this becomes a vicious cycle, which is made worse by user-initiated reloads of pages. And the situation gets even worse because some of the services that are submitting batch calls require all of the calls in the batch to succeed, or they rerun the entire batch. There's been no allowance made by a significant number of these services for partial success on batched queries. So the long and the short of it is, even after clients have timed out on calls, these calls remain in the database queue for processing, wasting already strained resources on useless work that the client's already timed out. So now we get to the actual congestion collapse, or in my words, getting up from the mat is harder than it looks. The database is in distress. We have hot nodes hosting high traffic items that aren't in the cache, and then we're caught in retry storms that are still storming. We've got about 98% of all DB requests are still successful within the 10 millisecond time period, i.e. anything that wasn't going to a node that was hosting one of the hot entities. However, despite 98% of all the queries hitting the database returning successfully, observed availability was way below that number because hundreds of the queries hitting the database to render a single page with no allowances for partial success or partial rendering. There was no concept of, for example, I have a shirt in many colors. If I can't query what that looks like in blue, I can still probably render the page. But for reasons on the architecture, it would treat that as a full render failure, despite the fact that you have 99% of the content available for a page. So the retry storms are continuing to cause transactions to continue to queue. There are no runbooks or tooling available to purge the database queue of all its transactions other than the restart of the impacted nodes. And forcing that restart is going to nuke the local cache and the database queue, forcing slow disk reads to repopulate the entire cache. While you can conceivably try to nuke the queue that way, there are drawbacks to nuking the queue that way. And is the cure worse than the disease? It's hard to tell, especially when you're in the middle of it and you don't have a runbook to help you out. In addition, something that was not known until afterward was that the TCP receive window on the database had a 1 megabyte limit per TCP connection, leading to another 1,000 or so transactions invisibly queued from each connection from the routing layer to each one of these hosts that is dealing with this. So we have effectively thousands to millions of extra transactions sitting in a queue that we can't even see, because it's a TCP queue and not even a database queue. So restarting the database nodes isn't even enough to get us back on our feet, because we've got that queue sitting over in the weeds, threatening us menacingly, like the hammer behind its back, except we don't even know to go look at it. So the long recovery. Which caller was pushing more get key prefix calls than the entire cluster was designed to support? And we had no good telemetry to make this instantly obvious. Eventually, we did track it down, and the caller was throttled to effectively zero, reducing functionality on the retail site while vastly reducing the incoming load to stable. Numerous methods were tried to get the pending transactions out of the DB queue, but during the incident, we weren't available of the TCP receive buffer. The number of services that were hotfixed to drop retries to 0 was larger than both of my hands and probably both of my feet as well, if I was counting that way. And if it wasn't hotfixed to be a number of retries of 0, it was hotfixed to max out at 1. 3 hours later, the hot nodes are useful again after load has been sufficiently reduced that the queues return to manageable levels. So what do you do about this? How do you prevent this sort of thing going forward? In this case, the retry logic was changed to understand the reliability of downstream systems. It is more beneficial to the enterprise to retry against reliable systems than unreliable systems. So if you're already down below 98% availability or 99% availability, or what arbitrary number you happen to want, the retries are more useful as trying to catch one-offs for high availability services. Otherwise, you're just going to add retries to the queue and add retries to the queue and add retries to the queue. And the numbers for most of these services, the second retry is functionally useless in almost all cases. You may have a different case, and if you're talking specifically about financial stuff, I can understand that that the number of retries and fidelity is much more important than the load that those retry storms can provide. But most applications, that doesn't hold true. So now the retry storm is about 1% additional load as opposed to a factor of 2, 3, 4, or what have you. The max queue sizes are now set to reasonable values for all known queues. You have no more infinite queues everywhere, and thought is given to right-size the queues and their impact on congestion collapse. You want to load test your services past max load. You want to test them absolutely to destruction so that you can look for unbounded latency increases. These usually indicate either an unidentified or a non-optimally configured queue somewhere that you want to get rid of or configure more properly. And the other thing is, after you have completely overloaded the system and tested it basically to destruction, how quickly can you recover? In this case, it took several hours to recover, even after we had removed the major offending sources of load. That's not what you're looking for. What you're looking for is a system which is capable of coming back up to its feet once the offending conditions have been removed, and you want it to come up in less than a minute. This is not practical for everyone, but this is the sort of thing that's worth thinking about in terms of, if I get brought completely to my knees, how fast can I get back to my feet? And it's something that most people don't actually think about in the design process. The routing layer to the database now organically caches frequently seen entities. You may ask why that didn't happen before, and I can't comment. Across the company, there were 11 separate postmortems that I am aware of, each of which had several action items to avoid a recurrence. So, like any good quality outage, it's almost always more than one thing that caused it. Or there's at least 4 or 5 different places where if Woody had gone right to the police, this would never have happened. And if you get that reference, good for you. It means you're probably my age. So what else did we learn? Random traffic variations are going to happen, and they are going to overload your service. You cannot prevent it. The only thing that you can do is plan for it. There's no way you can prevent this. So you want to invest in graceful degradation as a response to these overload conditions. You will have to fail some requests. Fail fast and fail using as little resource as you can, because if you're failing, you don't want to waste your resources telling people you failed any more than you have to. And just remember, it's almost always better to serve some users than none. Don't kick a service while it's ailing. Avoid retries to distress services. Send explicit overload signals back to calling services so that you can say, hey, back off. I'm dying here. You want to have a max retries of 1 or preferably less, because the second one almost never helps your availability. And you do want to make it so that you are aware of, hey, the service I'm calling is relatively healthy. It is safe for me to give a retry to this, and it may provide me some benefit. And ensure that you understand, are all of your callers failing, not just the calls on this particular host. There needs to be some sort of central clearinghouse worth of data to say, yeah, according to across the board, we think this is 98% available, so let's stop hitting it. Whereas one server may have 100%. You still want them paying attention to the, please don't poke the dead thing. And you want to be more efficient under high load, and you want to batch requests when possible. Choose the work done carefully. Don't do useless work, i.e. when you have stuff in your queue that's been in your queue longer than your client timeouts, discard it from your queue. It's useless work. Avoid it. Don't do it. And account for partial success to avoid having to retry the entire batch. So I have some take-home lessons, and I've got 30 seconds. So if you remember nothing else about this talk, remember this bit. This is the fun bit. There's no such thing as a safe change. You will have overloads. Plan accordingly. Don't kick a service while it's down. Avoid retries and selectively drop traffic to avoid a full congestive collapse. Send back explicit signals of overload. It also helps an awful lot if you understand what is your high-value traffic versus your non-high-value traffic. Stuff, if you know if you have a high probability on search applications that it's a robot, drop it. Who cares? Robot's not going to yell at you. People yell at you. Unbounded queues are going to come back to bite you, so find them, configure them. Assess risk versus cost intelligently. A performance dip is annoying, but lost data may be the end of your service and the end of your business. These are not the same thing. One is survivable, the other is not. Plan for disasters ahead of time, not during. Game days are invaluable, and they're even better when they actually let you break production. And invest in telemetry. If you can't see their misbehavior, you can't proactively respond optimally. If you can't identify who's misbehaving, mitigating impact is made very much harder. So I've probably overrun the Q&A. I have some contact information sitting at the end of the deck. Does anyone have questions for as long as he lets me stay up here?
All right, what questions do I have for David?
Yeah, you said it sends signals back to clients that you're overloaded. How do you do that practically?
Practically 503 codes are really good. It depends entirely on the application. There's service unavailable. There's also a service too busy HTTP return code. As long as your caller and the service agree on what an overload signal is, it can be literally anything. For HTTP, they're predefined. For a lot of other things, not so much.
I may have missed this in your talk about the e-commerce site. You said it was a sale that was globally launched all at once. Could
Yes,
we have
it
just
was.
turned off the sale, or is it too late?
If you have guessed successfully who the underlying company is, you would understand that no, you can't turn that sale off.
Okay. We were guessing back here, but I don't know.
The amount of advertising that comes in front of that sale starts weeks to months ahead of time. And like I said, we're talking about an e-commerce giant. We're not talking about a company. We're not talking about like Nintendo selling the Switch 2.